Hello, I'm Chris, and I'm going to present my topic tagging project for NLP. So the objective and outcomes of this project is to be able to tag documents. So give the model a document and it will output at which topic it belongs to. We will also compare multiple datasets over a same model and compare multiple models. So the method to get these datasets is to scrape Wikipedia or use Kaggle, and we will test the TF-IDF and BERT model over these datasets. So topic tagging is also called document classification. Its goal is to categorize a document into a topic, and this is done via AI or machine learning. So the techniques used include naive Bayes, TF-IDF, SVM, ANN, RNNs, and more. The application of topic tagging includes spam filtering, language detection, sentiment analysis, email routing, etc. And topic tagging can be done on text, images, audio, and more. We'll focus mainly on the text aspect of topic tagging. So the first research was done on word count. To train a word count model, we first need to pre-process each document. We will label each document under a topic, then build a bag of word common to all the documents from the training datasets. A bag of word is nothing more than a list of all the unique words in all the documents that were given to the model. Then, for each individual topic, we'll count the occurrences of every word in the bag of words. The counts can also be transformed into frequencies for every topic individually. Now, when a new input comes in, we need to classify it. So the first step is to pre-process this input with the same pipeline as the training. We will count the occurrences or frequencies of words according to the model's bag of words, so any new word in the input will be ignored. Once we have the vector of frequencies, we will find the closest vector from the topics and label the document as this topic. Word count has problems. If we don't use frequencies, different document lengths will just be unfair for the documents that have less words, because a relevant word from a document could be counted more times in another document just because it had more data. This can be easily resolved by transforming counts to frequencies. Another problem is the common words between all documents. Each time there is a common word, it's like the dimension of the vector got reduced by 1. Now, for the second model, TF-IDF, its goal was to solve the problem of the common word between all topics of the word count model. Its training just consists of the same steps as the word count model, but on top of that, words that appear in a different topic will be penalized each time they appear in a different topic. Now for the classification, it's exactly the same as word count, but TF-IDF also has its own problems because it does not capture position in text, which may be important sometimes. It does not capture semantics and context. It differentiates between synonyms, and it does not differentiate between homonyms. Then we have BERT. It stands for Bidirectional Encoder Representations from Transformers. BERT is a transformer-based language model developed by Google, and it has been trained on over 3 billion words. By default, BERT uses 12 encoder-only transformers with attention, and it was pre-trained on word prediction and sentence prediction. So the benefit of BERT is that it's a pre-trained model. We can just download the model. It uses machine learning, and as I said, it generates contextual embeddings. Now I'm going to talk about how I retrieve the documents. So the first data sets are for the word count and TF-IDF. So this model has three collection of labeled documents. Each topic in each collection has a list of articles, and all of these articles are merged into one per topic, of course. All these articles were taken from Wikipedia using Beautiful Soup. Now we have three collections for this model. First, we will use the two topics collection, which will either classify an input as either a programming language or a country, two very different topics. Then we will train and test TF-IDF on multiple topics. We can see that there is a lot of overlap between these topics. We will test how TF-IDF does with that much overlapping. The third collection is the same as the second, but with half the data. Now for BERT, we only have one dataset, which is one CSV dataset of labeled emails. Each email is marked as either spam or not spam. Initially, the datasets contain 500 spam email and 2.5 thousand non-spam email. This will cause an imbalance in the training data. So we reduced the non-spam emails to the same amount of spam emails. So first, the implementation of TF-IDF. To initialize the model, we pass a dictionary of topics with values as list of documents. This is what I previously called collection. Each topic's documents are merged into one document, and a bag of words is formed across all topic. Now for training, each document is pre-processed. Word counts are generated for each topic individually according to the bag of words. They are then normalized to get frequencies and appended to a matrix of topic word frequencies. Then each word's inverse document frequency is calculated. This is IDF. And then each word frequencies, which is DF, for each topic is multiplied by its IDF. And then each TF-IDF for every topic is again normalized. Now for classification with TF-IDF, when a new input comes, it is pre-processed the same way as training data. The word counts are generated for the input according to the model's bag of words. Word counts are normalized into word frequencies, but it's not possible to calculate TF-IDFs without having to change the model. Then the generated frequencies are compared by cosine similarity to each individual topic's TF-IDF vector. Each cosine similarity is appended to a list of scores, which is then normalized into confidences, and the topic with the highest confidence is displayed. Now for the BERT model. To initialize it, we just pass a data frame of documents and labels, and a train test split is generated from this data frame. So for training, we first built the following neural network. Of course, the model is fitted to the training data, which takes place over a given number of epochs. Now for classification, an input is given to the model, then the neural network is told to predict the label of the input, which will generate a score between 0 and 1. The closer scores to 0 are not spam, and the closer scores to 1 are spam. And in the end, we generate a confusion matrix over the testing set. So the results for the two-topic collection of TF-IDF is that it correctly classified all documents with known topics with an average confidence of 98%. I also tested 3 documents with topics that are not programming or country. It classified them all as country and some of them with even high confidence for an average confidence of 75%. As for the multi-topics collection, The TF-IDF model correctly classified all documents, again, with 6 known topics, but with a lower confidence of 72.5%. As for the reduced multi-topic collection, it again classified all documents correctly, with an average confidence of 70%, which is just a bit lower for half the data. Now for BERT, it stabilized at epoch 4 out of 10, and it reached its peak at epochs 8 or 9. In the end, it had an accuracy of 70% and a loss of 58%, which is okay. Now, as far as the results of BERT, it correctly classified 9 out of 10 emails, but the average confidence was only 30%. This can be explained by the fact that the data is very different to BERT model, as BERT was trained on books and Wikipedia articles that do not have spelling mistakes, while a lot of these emails have a huge amount of spelling mistakes. We can see that the primary decision feature is probably the amount of numbers and URLs in the text, since spam emails have a lot of those. But the confusion matrix shows rather good results. I finished with the presentation and now I'm gonna show you the code. So the first part of the code is initializing. Of course, we have the imports of the different libraries that we'll use. General functions such as reading from Wikipedia, mobilizing an array into an array of probabilities, and this is just a function to display a data frame. Now we will make use of NLP functions like removing special characters, tokenization, removing stop words, stemming, or lemmatization. Preprocessing is just the result of each of the above methods sequentially. We have a method to generate a bag of words given a text, and a method to calculate the word embeddings for BERT. The word embeddings are calculated using downloaded models from TensorHub. We can see here that the embedding of king minus man plus woman is approximately equal to the embedding of queen. So here are the two topic collections, which is either a programming language or a country. It's reading all these articles from Wikipedia. This is the multi-topic collection, which reads all these articles for programming, science, geography, biology, linguistics, and astronomy. And this is the reduced multi-topic collection, which is just randomly half of the multi-topic collection. Finally, we have the spam or not spam dataset, which looks like this, after filtering, of course. And now onto the models. The first model is TF-IDF. I'm not gonna go in details, but basically what it does is, like I said in the presentation, counting words for individual topic, then making a matrix of word counts, then it calculates the TF-IDF, and these are just methods for doing cosine similarity and transforming these scores into classifications so that will show the actual topic instead of just scores. So for binary topics, the two topics collection, we can see that the most frequent words for programming language are language, which makes sense, C, type, code, and function, while for country, it's country, world, state, new, and government. We can see that language is also common in country, which is normal since the articles should talk about each country's languages. So with TF-IDF, we want to reduce these common words. Now we can see that with TF-IDF, the top words are Perl, compiler, Lisp, PHP, and Fortran. We see that they have nothing in common with the country, while the top word frequencies have nothing in common with the TF-IDF, but have a lot in common with the top frequencies for country. The same goes for the top frequency word for countries. So it has more in common with the word frequencies for programming than with its own TF-IDF, while the top TF-IDF word for countries have more in common with the word frequencies of country than with the word frequencies and TF-IDF of programming language. So here we are testing programming languages, countries, and other articles. So it classified the article about Ada as programming language with a 96% confidence. Apache Groovy also correctly classified as programming language, and the same goes for MySQL and all the countries. It classified CAT as a country with a big confidence of 97%, particle physics also as a country with a confidence of 75%, and morpheme also as a country but with a lower confidence of 50%. So it looks like our model has a bias towards countries. The same goes for multiple topics. We can see that each topic word count has more in common with other word counts than with their own TF-IDF, while each topic's TF-IDF has more in common with its word counts than with other topics. Now, of course, there's a lot of common words in all these categories. So even with TF-IDF, we can see some correlation. So for example, we can see that science, TF-IDF words, have some commonality with the astronomy TF-IDF, since both rely heavily on physics. Now these are the tests. And again, I'm not going to go into details, but the accuracies were pretty high, except for geography, which seems to have low accuracies. Now for the reduced multi-topic collection, we're doing the same tests and we are getting a lot of common results. The top words are not exactly the same, but the classifications are all correct with, like I said in the presentation, an average confidence that is just a bit lower. Finally, for the BERT model, we're initializing the documents as a data frame, then doing a Turing test split, building the network with an input, dropout, and dense layers while using BERT embeddings. Then we're compiling and fitting the model and scoring and classifying the inputs and showing a confusion matrix. So here we are actually building a network with the SPAN dataset. We can see that it finished with an accuracy of 0.77, which is good. And here for classification, it mostly classified everything correctly except for one document. And the confusion matrix, as shown in the presentation, is rather good, but we can see that there are a lot of false positives and false negatives. Thank you for listening to my long presentation. I hope you enjoyed it.